Good morning. So I will present first, and this is on a project that is a collaborative effort between Imperial, Queen's University and Manchester Metropolitan University. So I started a little bit on the motivation, what actually drove us in the project. We're about 3 years into the project now, we're near the end, and what really drove us through this was 2 early observations. The first one on nonlinear crest amplifications in very steep sea states, and the second one on extreme impact loading due to slamming. So these 2 observations, I'll just have a couple of slides on each, just to give you some of the motivation. So the first one came out of an experimental study we did down at Imperial in our wave basin, and what we principally showed there is that if you have a relatively small significant wave height, so relatively small amplitude sea state, you will find that a radial distribution, a second order distribution, and the experimental data match very well in terms of crest statistics. But as you go into large amplitude sea states, you have radial here, so it's a linear solution, a forest still, so second order solution here, and then the experimental data is beyond that second order solution in terms of crest height. So you get larger crests than you would expect from any of the design solutions. So that's the first motivation, and the question really is, how does something like this translate into loading? So this is on crests, but how does it translate into loading in random sea states? The second observation was due to wave slamming, and this is now on the flap type device, and perhaps one would expect that in this part of the wave cycle, when a very large wave has just gone over the flap, perhaps one would expect a very large load at this moment. But actually what happens is, as the flap returns, there's a very deep trough forming in front of the flap. There's very little resistance from the water in front of it, and what you actually get is an impact loading where the flap hits into the water rather than the water into the flap. And these 2 observations really drove us through the project. So what I'm going to spend the next few minutes talking about is how we've made progress in really advancing our physical understanding of nonlinear load amplification in steep sea states, and then also impact loading due to slamming. The first one, we looked at what is effectively a heaving buoy, so you would have a cylindrical geometry, but in the first step to simplify it, what we said, okay, we are just looking at a 2D cross-section of that. So a 2D cross-section of a vertical cylinder would be a rectangular box. So we build a large model, it's about 3 meter wide, and one of the advantages of doing it in a 2D tank as well, you can do very long random sea simulations. We then build a rig that you see here. In this particular configuration, it's restrained so it can only move and heave, and then there's a load cell right at the top there, and so we're measuring the heave load, or in another setup we would take the load cell out and let it freely heave and measure the heave displacement. So looking at the heave forcing first, I'm going to try to explain this now in detail, this plot. We have on this axis here the force, heave force, and it's normalized by the significant wave height. And on that axis we have probability of exceedance. The black line here is what you would get from a linear solution, say ramen, for example. The first black line here, the thinner black line, is then the heave loading you would record on the experimental setup in a relatively small amplitude sea state. And as you then increase the steepness of the sea state, you'll see that actually what happens, the heave loading increases more than proportionate. So if this was a linear system, then these 3 lines should all collapse on the linear solution. But in a nonlinear sea state, what you actually see, you have quite some large load amplifications which can reach up to about 30% in a relatively steep sea state at probability of exceedance of 10 to minus 3. The question then is, how does that relate into the motion of the box? And actually, surprisingly, or perhaps not surprisingly, you get the opposite trend. So you get load amplifications, but if you now look at these lines, they're in exactly the reverse order as these lines. So the smallest amplitude sea state is closer to the linear solution. And actually, as you make the sea state steeper, you get less and less motion. You get more forcing, but less motion. And what you can imagine is, as the box moves, on the underside you will get a lot of vortex shedding, and that vortex shedding actually leads to more motion reduction than the motion increase you would get from increased forcing. So we looked at that in a bit more detail, and what the left-hand side plot shows you is the forcing spectrum, and you see in the forcing spectrum you have a lot of second harmonic and also higher harmonic. So this peak here you see, one is the peak period of the spectrum, and at about 2, actually slightly beyond 2, you get very significant second harmonic forcing content. But when you now look at a relatively large structure, this structure has so much inertia that none of this forcing actually feeds into motion because there's just too much inertia in the system. So that's perhaps something one would expect. A probably slightly more interesting part of it is this is now 2 individual motion events. The top one taken from a small amplitude C state and the bottom one from a large amplitude C state, but both of those have the same probability of occurrence, 10 to the minus 3 in this case. And what you can see, perhaps through observation, it's difficult to see, but the top one is from a much more broad-banded response, whereas the bottom one is what I would call a much more narrow-banded response, a much more regular wave pattern. If you then look at the actual response spectrum, you will see if you have a relatively small amplitude C state, you get really 2 parts in the response. One response naturally where you would expect it at the spectral peak period, but also you get the resonance coming through. So you can see at higher frequencies you have the resonance of the structure. That second peak is actually where the resonance of that structure lies. Whereas if you look at very large amplitude C states, because you have now so much vortex shedding in those large motions, they're particularly attenuating the resonance. And you see the resonance would lie about here for the structure, but you don't feed this resonance through at all. And that's an observation that's quite common to all the measurements we've taken. So it's really, resonance is significantly damped in large amplitude C states. So we've done a lot more observations there, a lot of different random wave C states, tested in about, so it was in excess of 150,000 individual wave events. What we're doing now in this is trying to get more representative simple solutions. So the second part then of the work is really on the surging type device, on the flap device, and this is very similar to the oyster 40 scale. And what we had done early on is looking just at the global load. So have a 6 degree of freedom load cell right at the foundation of the structure. What we've done more recently is then embed pressure sensors in the front of the device. You see them here and also laterally across. And what we can see from that is, looking now at the pressure trace on the flap, you see the very largest pressure trace, the red one, would occur very much towards the root of the device. This is where the first impact happens. But once you have a number of sensors, what you can now actually build is a map that goes in both space and time. So you have time on this axis, and on that axis you have, so this would be the root or the hinge. And as you go further up, you get towards the top of the flap, and you can see how this impact event travels along the flap. And what we've then done is look, how does the impact event or the size of the impact correlate with, for example, the wave height. What you see at the top there is wave height versus slamming pressure, and there's a lot of scatter. So there's no real clear correlation that says if you have a larger wave hitting your flap, you get a larger load. It's very scattered, the data. If you then look at the data in a slightly different way, so now we have the velocity of the flap, so this is the maximum velocity of the flap rather than the wave height, you see there's a very clear correlation between the maximum pressure and the velocity. So that confirms that the mechanism is much more due to the flap hitting the water than a large wave occurring and hitting the flap. So the last piece of work I'll very quickly then talk about is we've done something very similar numerically. So we've built a mesh here which is highly resolved, and it's also a sliding mesh. It has a dynamic mesh for the rotation of the inner cylinder, and the crux of this part of the work now is a comparison between a compressible flow solver and an incompressible flow solver. So these are some very heavy computations, 12.5 days on 64 CPUs. What you get is this one here. Okay, let us come up a bit. I think the next one is quite interesting. What you will see now, just before, now actually it has a relatively large velocity, and I think it comes back again. Just before, now you can see it again, it accelerates against this void, hits the flap water surface, and leads to very large pressures. And again, the key of this is now that if you apply an incompressible solver, so that's the green line, you don't actually see that impact event. So a compressible solver, generally speaking, would not be able to capture that. If you look at an incompressible solver, so the red line now, you can see that you get actually slamming events which are very similar to what we've observed in the experiments. Perhaps if you saw earlier on my slides, we saw maximum impact pressures in the order of 8 kilopascal, and that is very well represented here. Okay, so the key there is the flap motion, so the global device motion is well captured by the incompressible solver, but the impact loading is not. Okay, and that brings me to the end, and I'll take any questions if I have any time left.
This production is brought to you by the University of Edinburgh.